All right. What's the difference between the equations on the right, nope, sorry, left, and the equations on the right? Okay, so yeah, what's isolated? Yeah, so we got the y by itself, right? All right. Can we take the derivative of the ones on the left? Actually, we've done those already. We did those in the last class. Could you do the derivatives of the ones on the right? All right, so from what you know right now, we'd have to rearrange them, right?
Yeah.
All right. So let's do the first one. Let's do this one. I'm going to rewrite it, don't worry. So we got x squared plus y squared equals 25. Right? Yeah. What is that if you were to graph that? Yeah. All right, so is it a function? It's not, because it's going to fail the vertical line test, right?
Yeah.
It's going to fail the vertical line test. So it is not a function. All right, so that's the other thing we're looking at is like if you look at those two things, some of them were functions, some of them were not. So that can make a difference here too. So let's solve this for y. So we've got y squared equals 25 minus x squared. And we do the square root of it. So y equals plus or minus the square root of 25 minus x squared. All right. So, what do we have to do now? Right, we now have two different equations, right? So I've got, let's look at the first one. So I've got y equals the positive version of it, so 25 minus x squared. All right, so how do we do this one? Yeah, we have to do the chain rule. So I'm going to make u equal 25 minus x squared. So u prime is negative 2x. Yeah. And then we have y equals u to the 1/2. So y prime is 1 over 2 square root of u, right? That's the whole one that we always seem to be doing. And then u prime. So y prime is 1 over 2 square root of 25 minus x squared and times negative 2x, so I'll just put that on top. So I've got negative x over the square root of 25 minus x squared. And if we did the other one, the only thing that would change is there was a negative sign in front. So your sign would change basically. So in essence, if we did the other one, it could end up really being plus or minus that. Not horrible, right? We could do that. All right. What about this one? Isolate the y for me. Would somebody try? Did anybody get the y by itself? All right. What did we try? All right. So if I did this. It's not quite a cubic. If they were squared, you might have a quadratic that you could work out. But it's not a cubic, unfortunately. So it's like I can take out 1y, but then I'm still left with 6x minus y squared. So even if I divide that over, I'm still going to be with the y squared, right? All right, so there actually is no way to solve this one to get the y by itself. So we have some situations like this one where you can't. And all the other rules of differentiation would still work, and you can use it. Sometimes they're going to be hard, but you can do that. We do have some situations where it's not a function and you just can't. You cannot isolate the variables, right? That can happen. And we saw that even like with the h's and stuff like that, we were doing it. Sometimes you just could not isolate and get the h completely by itself. So we still had stuff left in there. So we've got to look at another method of differentiation. So what we're going to look at is known as implicit differentiation. So it's actually a play off of the chain rule, right? And what we were looking at, as you remember, when we were doing these, notice how I kind of wrote this as 1 over the square root of u, then I put u prime there? Because we were technically u was a function that I had to do the derivative of it. We're going to do something very similar when we're doing this. When we're taking the derivative of y, you're going to multiply it by y prime. Unlike with u prime, where we actually had something to put there, the y prime we're not. And at the end, we're going to pull the y prime out, and that's going to end up being our equal piece. So let's look at actually this problem using implicit differentiation, see if we get something similar to the answer. So we've got the x squared plus y squared equals 25. So what we're going to do is we're going to take the derivative of both sides. So we're going to do the dx of x squared plus y squared equals the dx of 25. So this side, now we're going to take the derivative of 2x, which gives you what? Nope. Right, it gives you 2x. So actually, I'm going to rewrite this. I'm going to split this out. All right, so this one becomes 2x. This one becomes 2y and then dy dx. Because now the derivative of y, that's what the dy comes from. And what's the derivative of 25? 0. All right, so I've got 2x plus 2y dy dx equals 0. So I'm going to move over the 2x. So I have 2y dy dx equals negative 2x. I'm going to divide by the 2y. So I get dy dx equals negative 2x over 2y. So dy dx is just negative x over y. Yeah, depending on how. If you learned it after integration, you actually learn differential equations, which is similar to implicit differentiation. They're very, very similar in how it's done. Because I actually do that in Calc 2. After we do the integration, we do differential equations. Because they haven't been assigned yet. So basically what happens is the schedule came out. They're going to go through and all the full professors that are here will pick the classes they want to teach. And then anything left over, then they go to the adjuncts. And then they assign those. So, So depending on which one you're going to pick, they actually should have those assigned because they just came out. So normally by like around the end of October, beginning of November, we'll have those assigned. And we'll start to see them, and I'll know which one I'll have.
I'm supposed to pick my practice on Friday.
Oh Jesus! Why?
The coordinator for the scholarship wants it done.
Gotcha.
As soon as possible. And we were supposed to the thing was supposed to be released on Monday, so we're gonna have at least a week.
Yeah.
Yeah, I was doing it during programming class, trying to make the schedule fit.
I have taught Calc 2 for the past 5 or 6 semesters, but since my schedule, I can teach technically any time now. I don't have to necessarily just teach at night. I'm not sure what they're going to give me yet. So, as soon as I know, I'll let you know because worst case, you can always switch. So.
I mean, I'll just check when
Yeah. So I'll know which ones I'm teaching before they're actually posted up there, though, so I can let you know. So, all right. So let's look at. So does this look like that? It's kind of close. Okay. So the x is there, right? But that bottom part's not there, right? Okay. It is y. So, very good. So we had basically y prime is negative x over y. And my original problem was x squared plus y squared equals 25. If I solved that for y, which we already did, and replaced it, I get the same thing. So that's why it doesn't look necessarily the same, because remember, y is a function. So y has a value in that case. So if we were to take the original problem and solve for y, which in some situations we're going to do to be able to plug those things back in, that's what you'd actually replace. And it does come out to be the exact same thing as the other thing. All right. So they do. And then actually what you would do is you just go this and just put the plus minus up top because it'd be reversed to the opposite one. All right. Now let's look at that other problem that we couldn't do. And yeah, we're going to do B and C for this one too, but we're going to do A first. So we've got x to the third plus y to the third equals 6xy. And you're going to notice there's two different things. Like when we're looking at like this method, like the dx and stuff, that's Leibniz notation. If you use the y prime, that's Newton notation. So it just depends on which one you like better when you're doing it. I'm going to show you actually Newton's notation for this one because I actually think it's a little cleaner when you're doing these. You just have to remember that y prime is not y raised to something when you're looking at it. All right, so we're going to go through and we're going to find the derivative of each piece. So the derivative of x to the third is 3x squared. The derivative of y to the third is what? Three y squared. Yeah, I'm just going to use y prime. Yeah, you can do dy dx. I'm going to use y prime. It's cleaner for this one. All right, what about the 6xy?
It's how
So I've heard 1. I've heard 6y prime.
it's what's it called? Oh my, no, not power. Quadrant.
It is.
See, I'm good.
We have to do this as the product rule. Okay? When we were doing the ones before, remember, we basically looked at any other variable as a constant. So in that situation, 6y would have made sense. Okay, because we would have just gotten rid of the x at that point, 6y would have been left. But since we're actually doing the derivative of the y and we're using that, we need to actually look at this as a product. So that means the derivative of the first, which will make the first 6x and the second y. So the derivative of 6x is 6y. Plus the derivative of the second, derivative of y is y prime times 6x. So actually I'm going to rewrite this. It's a little cleaner. All right. Everybody get this side? That side's pretty straightforward. Right? All right, so this one, when you're looking at it, we have to look at the two pieces. So if we have 6xy, so we'll say like f of x is 6x and g of x is y. So the prime, so f of x, so f prime of x is just 6. G prime of x is y prime, because the derivative of y is 1, right? And then you got to multiply it by y prime. So it's really 1 y prime. Does that part make sense? It's okay. Does this piece over here make sense or no? Because that's probably the most confusing part of the whole thing.
Yeah, no.
Yeah, so you get the f of x works, right? Okay. So the g of x, so let me actually change one thing to make, I think it's going to make it a little easier just to show you. As really, so like if I'm just doing the derivative of y squared, based on what I'm doing here, this would be, this is going to go to 2y times y prime. Because we do the derivative of y and it's times the derivative of y, the dy dx or the y prime. Does that one make sense? Okay. So in my problem, I just have y. What's the derivative of y? Is 1 times y prime. That's why I was like, I think like I knew exactly what the mistake was. So I was like, let me do something with not that does not come out to be 1, and I think it'll click. All right. So that's where we get the. So the first one is the derivative of the first times the second. So that's where the 6y comes from. And then it's the derivative of the second times the first. So that's where the 6x y prime comes from. Okay? All right. Now, I need to isolate my y prime. So I'm going to actually delete this. Actually, yeah, we'll delete it where we had. All right, so what do you notice about all these right now? Does every problem, the entire problem, does it have something in common? Or no? We have a couple with y prime, but they all don't have a y prime.
Wow.
Yeah. Yeah, I can divide them all by 3. While that might not seem like a huge thing, it gets rid of stuff that I don't need. So if I divide them all by 3, I'm going to clean up some of the numbers. So this becomes x squared plus y squared y prime equals 2i plus 2xy prime. Yeah, just divide. It's just like multiplying everything by a number. I can divide everything by a number. As long as I do the same thing to both sides, doesn't change the problem. All right, now your next goal should be to get the y primes, like you guys are trying originally with this problem with the y's, getting the y's on one side and the x's on one side. Let's get the y primes on one side and everything else on the other side. So I'm going to move the 2y over here, so I got x squared minus 2y. And the y prime's over to the other side, so I have 2xy prime minus y squared y prime. Nope, because it's always going to be y prime. So, and the problem that when you guys were originally trying to do this, you had y to the third and a 6xy. There was no way to pull out all of the y's to get them together. So in this situation, it's always going to be y prime. So as long as I get all the y primes to one side, I can always factor out that y prime. So there won't ever be a situation where you can't get the y prime by itself. Yeah, this comes out to be nice. All right, so now we can on this side we can factor out the y prime. So I have x squared 2y equals 2x minus y squared y prime. What? And now that we've got, it's just multiplication. How do I get rid of the multiplication? I divide. So I have x squared minus 2y divided by 2x minus y squared equals y prime. And that's my derivative. Make sense or no? Okay. Huh?
I figured out a squared side stable.
Gotcha. All right. Yes. As I said, once you start to look at the very first problem, it's like with the dx, the ddx, I think makes it look a little more confusing than it is. I really like using the y primes with these. I think it actually works better. But I also like when I'm explaining it, showing you both so you can actually, because some people like one way or the other, and sometimes you'll see an example in a book that'll be written one way or another and not both. And you will see the dy dx quite often, especially if you do Calc 2 and you look at the differential equation, you're going to see dx and dy all the time in that situation. They don't use y prime at all. So just little things to keep in mind. Yeah?
Question.
Yep.
Does the Calc 2 is the Calc 2 technically the same as Calc 1?
Yes.
Okay, that's cool.
Yeah, you actually should be able to use that same textbook for Calc 1, Calc 2, and Calc 3. I think differentials, though technically they could use the same book, I think they do use a different book. Yes, so there's 3 calculus classes and they all use the same textbook, which is kind of why we pushed for the 9th edition now, is because we're going to start using that in the other ones. It's one of those ones we have to turn over at some point because you just go right through it. So in next semester, they were going to make the Calc 2 classes use the 9th to 10th, and so they just made everybody use them this semester for Calc 1. So it's actually, out of all the books you buy in school, it's probably one of the most good for your value because you get 3 classes out of 1 book. If you take all 3. Huh? Yeah, unfortunately, yeah, it doesn't. And that's why I don't like using them.
Yeah.
Because, yeah, they don't work. All right, so we've got that equation. Are we good to that equation now? Because we still got 2 other parts of this problem we have to do. All right, so this problem had 3 parts. The first part was to find the derivative. We did that. The second part was to find the tangent of, now this equation actually is a very special one. It's called the folium of Descartes, or Descartes. It makes a nice little loop-de-loop if you graph it. So we want to find the tangent line to it. You're going to do the tangent line the exact same way we did everything else. We have the derivative, you plug the values in, you find the slope, and then we write our equation. So we've got our equation. So we've got y prime equals x squared minus 2y over 2x minus y squared. And my point that I was looking at was 3, 3. So we're going to plug in 3 and 3 for both of them. So y prime equals 3 squared minus 2 times 3 over 2 times 3 minus 3 squared. So we get 9 minus 6 is 3. 6 minus 9 is negative 3. So you get negative 1 as my slope. Now we can use the point slope equation. So we got y minus 3 equals negative 1 times x minus 3. So y equals negative x plus 6. So there's our tangent line. Yeah. Desmos actually is nice when you're trying to graph like the crazy equations. It was x to the third plus y to the third.
I go with x squared.
No, I think they were both to the third. Yeah, they were both to the third.
What?
That's what it looks like. And then we just found our what was it, y equals negative x plus 6. So there is our tangent line at 3, 3. So, and if we were to graph our derivative of this, what was it? It was 2x. I want to make sure I got the signs right. That was it. It was x squared minus 2y over y squared minus 2x. Really? Actually, you know what? I can just do it this way. Yeah, we'll just do it this one. So there's the derivative of it. Yeah. Well, that's what, when you start getting into things that are not functions, you can get some crazy graphs. One of the things that, like, and we never actually covered it in our the pre-calc class here because there's so many other things to cover in such a short amount of time. But if you do take Calc 2, you will look at polar equations and parametric equations, and you can get some really cool graphs doing polar and parametric equations. So, because they just completely break down the function rules. You don't have to worry about x's and y's anymore. So it's kind of cool. All right, so we've got that. We've got our equation. The last piece of this question was to find at what point in the first quadrant is the tangent line horizontal? So horizontal would mean what? My slope is 0, right? So if I'm looking for a slope of 0, I want what do I want if I want my slope to be 0? Yeah, so my y prime equals 0. So I need this to equal 0. So that means that the top has to be equal to 0. So x squared minus 2y equals 0. All right. So the question is we need to solve for what? So y equals x squared over 2. That make sense? No.
Oh.
This is Calc 1. Nothing's that easy. No, I'm just kidding. Some things have been that easy. All right. So
Why did you get x squared on y over 2?
I subtracted the x squared and I divided by negative 2. Got it. You sure? I don't like the sly grin. All right. Okay. So we now can take that and plug it back into my original equation. So I have x to the third plus 1/2. Yeah, we'll do it that way. They liked it that way. I don't know why. To the third equals 6x 1/2 x squared. So I've got, let's see. How does that simplify to x to the 6th? Or 16x to the 3rd? All right, we're going to figure this out because I'm looking at it like I'm not sure how this actually works. Let's figure this out. So I got x to the 3rd plus, I know how to do it. 1/8 x to the 6th. Now I got how they did it. Is 3x to the 3rd. So we're going to move the x to the 3rd over. So I got 1/8 x to the 6th equals 2x to the 3rd. Multiply both sides by 8. And I get x to the 6th equals 16x to the 3rd.
Did you define? I don't know.
Which step?
It is just, I don't know how you said you would move over the 3x cubed, but and now 1/8x to the power of 6 equals
Right.
2x.
So we got 3x to the 3rd minus 1x to the 3rd.
Oh.
That's 2x to the 3rd. Don't worry. When I look at, like, the book literally goes from here to here. And I'm like, how did I get there? Until I started doing it, and I'm like, oh, that makes sense. So yeah, it's like there's a third to there. This is stuff's missing here. So yeah, move the x to the 3rd over and 1x to the 3rd. So that's why sometimes the book's good and sometimes it's like needs a little more explanation. All right, so we can take this, and we got x to the 3rd equals 16. So x equals the cubed root of 16. And if we plug that back into, so I'm going to actually clean this up a little bit. So x equals the 2 to the 4/3 root there. And if we plug that back in for y, we get x to the, or we get 8, 2 to the 8/3 divided by 2.
How did you get 4 thirds? Wouldn't that be?
16 is 2 to the 4th.
Oh.
So we've got x and y. And that's the point where the horizontal line is tangent. So the only reason we did that was because trying to plug in the cube root of 16 into here, or into here, would have been a little messier to do. By changing it to the 4/3, we can use the power rules for the exponents, which makes our life a little easier. So the point where it is, the horizontal tangent is at, is 2 to the 4/3 divided, and then 2 to the 5/3. If we look at this graph here, it'd be somewhere right around, I don't know, it's not going to let me actually do that on there. Yeah, it's not going to actually let me put on it, but. There. So we'll turn this one off. That's about where the, that looks like it's about horizontal there. No problem. So, yeah, that's where the slope would be 0 on that part. And we were only looking at the first quadrant, because if we were looking at other ones, there'd be another, the 0 is probably down here, and then there'd be an undefined one over here. Yeah, vertical slope. That's when you do the exact same thing, except the bottom would be 0. That's how you find your horizontal, or I mean your vertical ones. All right. Back into what y equals. Because remember, we got y equals x squared over 2. So I just plug the x back into that. And that's how I got the 8/3, because it was just 2 times the 4/3, which is 8/3. And then we subtracted the bottom 2 to get the 5/3. All right. Take your shot at this one. So let's do this. The green side's pretty easy because that's just a product rule. So let's look at that one side first, and then we'll deal with the other side, which actually is really easy, but most people are screwing with the x plus y. So if we look at this side, we've got f of x, or it sounds weird doing f of x is y squared, but it's fine. Not mathematically correct, but it'll work. So that's 2y y prime. And then g of x is cosine x, and boy, is it raining. And that's negative sine x. So my green side comes out to be, it's the derivative of the first, so 2y y prime times cosine x. And then it's plus derivative of the second, so you've got negative sine x times y squared. Now if we look at this side we just have to actually do the chain rule. So we're going to make u equal x plus y. So u prime is 1 plus y prime. And then sine of u is cosine of u prime. So I get cosine of x plus y times 1 plus y prime. So now our goal, once we've got everything done, our goal is to get the y primes together on one side, everything else over the other side. So that y prime I can pull out. What about this one? What do I got to do this side to? Yes. So we're going to distribute this piece here to both parts. So I've got cosine of x plus y plus cosine of x plus y prime equals 2y y prime cosine x minus y squared sine x. Now we can move the y primes to one side and the other stuff to the other side. So I have cosine x plus y minus or plus y squared sine x equals 2y y prime cosine x minus cosine x plus y prime. It's funny. All my years in college, I never understood why the professors had those boards that you could just slide up in the classroom, like in the big lecture halls. So I started doing calculus and teaching, and then I realized that's why, because they could just slide the problem up and keep writing. It's like, yep, be nice. Although Brian Kennedy really gets a kick out of me doing this. Like, you know, copy, pull things over to the next slides and stuff. All right, go ahead, ask. You said so I figured there was a question coming after that.
I was
Okay. So we're going to pull the prime out of this side. So I've got the cosine x plus y squared sine x equals y prime. And I have 2y cosine x minus cosine x plus y. And now I can divide. So cosine x plus y squared sine x divided by 2y cosine x minus cosine x plus y equals y prime. And that's my derivative.
You go back.
Yeah, I can go back to slide. Here?
Yeah.
Nope, because that times 1 is that.
Oh,
And then that times that is that. I know sometimes it's when the one's like, it's like, wait, that just came down. It's like, but the 1 was why it just came down.
So,
Yeah.
at the end, would you be able to cancel out those ones that you just said?
No. That was going to be my next. That was going to be my one little thing at the end of the. Before I switch back. Everybody good with this slide? Because I knew somebody would want to try.
Oh, why can't you do
You
that?
can't cancel these out because it's not in multiplication.
Now,
It's like, yeah, you can't cancel those because it's not multiplying. So, yeah, there's no way to do that. There actually is rules where you can split up the cosine x plus y and actually change them to something else. The addition of angles rules, but it's not going to make this problem any easier to look at. So leaving it like this is fine. So, if the plus and the minus were not there and there was multiplication, yes, you could cancel them out. But the plus and the minus kind of prevents it. Yeah, it'd be nice. All right, this is what that graph looked like.
Oh.
There's another graph.
Oh. That's cool. You kind of went through like a.
That's sine of xy equals sine of x plus sine of y.
what's those screen faces?
Yeah.
A 5-year-old drawing.
There's a little ghost.
Yeah, that's
Well,
screen
it
faces.
was like,
Yeah.
you know.
It's like fur and dog.
Yeah.
Oh,
It's like, and as you go further out, see, it's like it actually,
Oh.
it's circles.
yeah.
They're straight.
It can't even actually, like, so it actually starts to pixelate because it can't actually calculate that fine of detail.
Oh, I thought it said they can't process it.
Yeah, as it says, this equation contains fine detail that has not been fully resolved.
Why that's funny.
So, all right. As I was saying, when you start to play with non-functions in those type of equations, you get some really cool graphs. All right. Last thing we're gonna do, because I can feel your brain's already starting to hurt. So, it was hurting before you walked in the door. All right. How do I find the second derivative?
Do the same thing.
Yes, twice. All right, so to find a second derivative, before we can even find the second derivative, I have to find the first derivative. So find me the first derivative of x to the fourth plus y to the fourth equals 16. This one's not overly complicated. So,
And then you have to do that for the last problem.
and then I'll show you how to do the second derivative. actually. I go step back. That should be your first derivative. No chain rule, no anything else. All right. So, to find the second derivative, I'm going to do the derivative of this problem. So y prime was negative x to the third over y to the third. So we're going to do the derivative of that. Now this is a quotient. So we have to do the quotient rule for this one. So I've got, we're going to make f of x negative x to the third. So f prime of x is negative 3x squared. G of x is y to the third, so g prime of x is 3y squared y prime. So this right here, we know. So g prime of x is 3y squared times negative x to the third over y to the third. So g prime of x is negative 3x to the third over y. So remember, whenever you're doing the derivative of a y, we have the y prime, right? So the derivative of y to the third
Oh, you substitute
is 3y squared y prime. I know what y prime is.
Oh.
So I substitute that back in. So y prime is negative x to the third over y to the third. So we can simplify that down. We get negative 3x to the third over 1. So now we can do our quotient rule. So we've got derivative of the first, which is negative 3x squared, times the second, which is y to the third, minus derivative of the second, which is negative 3x to the third over y, times the first, which is negative x to the third, all over y to the sixth.
So is it like 3x to the power of 6 over y?
Yes.
Okay.
Actually, yes, it's going to be,
Positive.
yeah. Well, no, it's actually still going to be negative because there's 3 negative signs there. All right, so let's clean this up a little bit. So we got negative 3x squared y to the third minus 3x to the 6th over y all over y to the 6th. Yes, there's actually more we can do.
Not the y.
Yeah, because I got a fraction over a fraction, which is never a nice thing to leave.
Oh, complex.
Yeah, we never want to leave complex fractions if we can. So I can go back if you're not finished writing. There. Yeah, it's really easy to mess up and having. Did I screw up and have an extra negative sign in here when I shouldn't?
No, it's just I just moved mine. I just moved out the other. I did it in another place. Because I put where the y where the 0 was, so that would turn that negative. And I put it back.
Gotcha. That's not. I'm just making sure because I think.
No, yeah, it's just
You're fine.
yeah, it's just the same thing. Thank you.
Oh, I'm looking at their signs in the book, and I'm like, their signs are off of mine because they pull out a negative sign. I'm like, wait a second, how'd they get a plus? All right, so one of those things like they skip steps. All right, so we need to get the y's together, right? So we've got a y on one, but not the other one. So let's change that so I have y on both of them. On both of them. So I'm going to make this negative 3x squared y to the 4th minus 3x to the 6th all over y to the 6th. Which I'm then going to make negative 3x squared y to the 4th minus 3x 6 over y to the 7th. Because I have the y underneath that. So if I divided this by y, I have to put something at the top same, otherwise it changes it. So that's why that y to the third became y to the 4th. And then in essence, you can just literally move it down the bottom because you're multiplying by the inverse of the bottom part, and it just works out. This is one of those problems that I would say, like, if you got it to this point, you're probably pretty good. Because the next step that the book has, I'm going to show you, it's not nearly as intuitive. Like, if I didn't see it, I probably would not have thought to do this. And this would be fine. So they actually pull out a negative 3x squared. And they're left with y to the 4th plus x to the 4th over y to the 7th. The reason they did that, that's my original problem. My original problem was x to the 4th plus y to the 4th equals 16. Exactly. So they literally changed that to 16. So the final answer is negative 48 x squared over y. There's so many places that you can screw this up. It's not even funny. So it's like, go through. I pretty much wrote every single step out for this problem. I don't think I actually skipped any. So go through, look at the signs, at the exponents, because those are the ones where you're going to make your mistakes. All right. And if you can at least get down to this, so this is the same. That's the total. But if you get down to this, that you're pretty good. So, all right. Pause. Yes, there's supposed to be a 7 there.